So the reason we are investigating viscosity is that our final two locations that we're traveling to, Hawaii and Japan, are both volcanic areas. And so since lava, once it's out, we call it lava. Inside of the earth, it's called magma. Since melted rock is a liquid, it displays different viscosities or different resistance to flow. I'll tell you, when I say the word viscosity, I always have to think this R word, resistance. So you had the opportunity to watch Mrs. Shields show you the flow rate of three different substances: peanut butter, oil, and honey. And you had to watch all three first before you did the rankings. You should definitely be in agreement with me. If you aren't, fix it. Oil had the easiest flow, honey, medium, and peanut butter was the most difficult. You could see that. Now, what you had to think through is, well, what does that mean about its viscosity? Now, in your mind, get this again. What R word do we use to define viscosity? And that R word is resistance. So which was the most resistant to flow? That would be peanut butter. So you should have put high viscosity there. The least resistant was the low viscosity oil, and then honey was in the middle. Now, how does this apply to what we're going to be studying? If lava's like oil, it would flow out of the crater easily and down the slopes of the volcano. But if it's more like peanut butter, it would not flow easily out of the crater and down the volcano's sides. So you're probably wondering at this point, well, what is it that really determines the viscosity of magma? And there are several factors, but I'll tell you there is one secret ingredient. And that secret ingredient is right here. You've seen these two pictures. You might recognize this from our egg carton as stone number 4. This is a perfect pure quartz crystal. And quartz is silica. So its mineral name is quartz, but its chemistry name is silica. And silica just has silicon and oxygen. So it's the most common silicate mineral in continental crust. So anyway, when you look at this picture of silica, and then look at it with a micrograph, which is a microscope view. I know this might have been a little hard without my guidance, but do you notice as I outline, can you see the hexagon side there? Then you see a bottom point here and a bottom point here of a different silica molecule. Now, when you're looking at that micrograph, do you think there are big gaps between them, or do you think they fit together tightly? That's what we're thinking through. So now, for question number 1 there, what do we see? We see a 6-sided hexagon with the quartz. And by the way, its color, pure quartz, is very light in color. It is clear. That's going to be important soon in our challenge you had. Now, what do we notice about the way that the silica molecules fit together? Because there are so many flat sides, they fit together tightly. Look again at this. See how the flat sides will fit right next door. So high silica in the magma means there's lots of molecules that can fit together tightly. So what do we think about lots of silica? So if you have tight fitting silica, will it flow easily or will it resist? Look at that again. If we have tight fitting silica in the magma, will it flow easily or will it resist? And you should be like, ooh, tight fitting silica will resist. High viscosity, remember, high viscosity means resistant to flow. So tight fitting silica makes the magma resistant. Now, I bet that this was your biggest challenge of this lesson. So one thing that we know to be true is that every stone has a story. And what we're just going to discover today is that if you see an igneous rock, the color of the igneous rock can tell you, was it like oil, honey, or peanut butter back in the days when it was melted. So it was a good idea really to work instead of normally left to right from right to left here. So we know on our planet that magma doesn't always come in the same viscosities. We can have low, medium, or high viscosity. So if it's low viscosity, it's not resisting flow, so it does not have much tight-fitting silica. So if it's low in silica, low in clear colored, light colored silica, then it's going to look dark. And this is the rock that should have matched. Now let's go to the bottom one. If you have high viscosity, peanut butter-like magma, that means it's high in tight-fitting silica, and it's going to look light in color. This was the most obvious, all light in color. Now this one, do you see those speckles of dark? So this would be the medium in all cases. And the reason that we say that is, oh gosh, look, If I have a dark colored igneous rock, I know it was really runny, low resistance, low viscosity when it was magma. But if I see a light colored igneous rock like this one, I know that it was more like peanut butter and was very resistant to flow. Now, we will be applying what we've learned about viscosity and silica in the magma as we travel to Hawaii and also